Thank you, everybody, for joining in, for taking the busy time of your day today and hopping on. We have an amazing topic today, which is reading the rock and understanding geology for your blast design. And there are several content that we will cover today, how this is one of the most impactful thing that can help in the design process here. To begin with, I'll just kick off with a quick introduction for today's webinar speaker, uh, Mr. Eli Williams. Eli has a degree in civil engineering from the University of New Hampshire. He joined main drilling and blasting while he was in school for an internship, and after graduating from his internship, he quickly rose from a drone pilot to a blaster, to a quarry engineer and a technical specialist. He has helped optimize blasting operations using the latest technologies in quarries throughout the northeastern United States. He has now joined Strayos with his hopes of sharing his experience from what he has learned in the field to how you can improve blasting safety and productivity in mines and quarries everywhere. With further ado, we'll just kick off with today's agenda here, which will go into more detail. But to give you a quick introduction about Strayos, is what we do is, for those who are not familiar, what we do is we are a software platform which has the tools built for each step of the value chain, starting from surveying, so you can bring your remote sensing data, such as drones or camera phones, and then you can plan out generate a 3D georeference model. And then within the same data, there are tools such as geology analysis, drilling and blast planning, to loading and hauling, and then various prediction tools on that. And then the post-blast side, you can run fragmentation analysis and reporting, along with that KPI tracking for various cost optimization initiatives that you may have. So that's in a nutshell. Won't go into much detail. From the workflow perspective, it's fairly simple. You capture a data, you bring it, you process it either online or offline, design it, get a report, and you have a full holistic view of your planning process. So essentially what it does, it helps you to a true digitized model of your blast planning process here. So the next kind of, I'll let Eli take over and introduce the topic for today and the agenda. And just a housekeeping here. If you have questions, type your questions in the question box you see just besides the chat. So type all your questions there. We will moderate at the end. If you have comments as well, type those as well. We will have 3 poll questions during the presentation, so we will release it as the topic comes. And then, yes, we love to get feedback about the webinar. So also please pass on at the end if you have any comments so that we can tailor based on those feedback. So without further ado, Eli, take it away.
Awesome. Thank you, Robbie. Yeah, so just to sum up, yeah, my name's Eli. I recently joined Strayos as a solutions engineer. My background is in the drilling and blasting field as a blaster and a field engineer, specifically in the quarry mine and quarry and aggregates in the Northeast United States. I put this webinar together to kind of give some references and guidance to conducting that shot design in the quarry atmosphere. And I'll use some examples and specifics from my background that can hopefully help you guys in the field. So to get going here, we're going to kind of look at our agenda, and we're going to look at geological site conditions on your site and some of the rock properties you might see and how to address those. We'll kind of move into blasting considerations, how these are going to affect your drilling and loading within that shot design. and how those geological considerations will also play a role in fragmentation and vibration in your drilling and blasting operations. So first off, we'll look at our site conditions. As a blaster and a driller, you get onto your site and you might have varying site conditions, different rock types, different applications on your site for outcomes. And, assessing these right off the bat, whether it's just visually or looking at any previous data you have for that site, is critical. Doing testing of rock can be costly, test drilling timely, and sometimes you just don't have those resources right at your hands right away when you get onto a site, whether it's a new site or an old site. So just kind of getting a handle of what you have in front of you, what kind of type of rock you're looking at, the properties of that rock, the densities, compressive strengths of them, and also what time of year it is. Depending where you are in the world, if you're dealing with freeze-thaw cycles, heavy rain or snow events, and changes to face conditions, slope conditions, these are all things that you want to be aware of, on a day-to-day basis, not only for drilling and blasting, but for safety concerns. Next slide here. So looking at your rock, there are a lot of references out there to kind of address, the quality of the surface of that rock, kind of what the face looks like. And I put a couple references here for you guys. The GSI, Geological Strength Index, rock quality designation, and the rock mass rating. These are some common geological indexes that you can reference that kind of shows the quality of the rock, whether it's jointed, seamy, fractured on the surface, at what level, and just kind of the overall quality of that rock. These are pretty widely known references. You can look up and reference for information depending on your site and kind of get a good base idea of what you're looking at when you're walking or analyzing a high wall or the geology on your site. So when we tailor this to blasting, depending on the quality of your rock, if you've never blasted in this pit or this site before, you kind of want to look at what powder factor you might be applying to this. And this can go several different ways, depending on your blast design. If you have a desired hole size or pattern that you're trying to accomplish, if you're regulated in any certain way by pounds per delay, understanding the powder factor, pounds per cubic yard, or kilograms per cubic meter, depending on how you're going to be shooting this rock and what level of explosives you're kind of applying to it. The weaker the rock, the less of a powder factor you'll need. You can see on the left here, difficulty of rock breakage ranging from low to very high. This correlates with the appropriate powder factor for that type of rock. Typically, you see in hard granites, you'll see a hard powder factor upwards of 2 pounds per cubic yard, where some low hero rocks, some people like to say, easy to break, doesn't take a lot of energy, you'll see a lower powder factor in below 1 typically for pounds per cubic yard. So kind of understanding and testing, knowing what that rock is, will kind of help you apply an appropriate powder factor to your blasting applications. So we got our first poll question here. Robbie should launch it. And that question is, what sources of geological data do you gather before drilling and blasting operations? Just kind of curious to see, what you guys are acquiring for information out there, where that might be. Is it helpful to you? Are you looking for more information? Just kind of get an outreach on what is out there across the world. So we'll take a second, get some feedback here.
Yeah, so there's a good mix here. A lot of the responses from info from geologists. We'll give another 10 seconds or so. While everybody's responding, wait, we'll give another last 3 seconds. Great, we'll close the poll. Thank you, everybody, for participating.
Awesome. So we'll kind of look at some sources I've gathered to share with you guys today. If you're in the United States, The USGS, United States Geological Survey, posts a great source for kind of finding a geology within your state and region. It's very interactive. You can download it over Google Earth and kind of see formations and within your state where they might be and how that correlates to your site. I found it as a useful tool just for a quick reference to see, if you're getting to a new area, a new site, unfamiliar, and just kind of see patterns within the region of your state, where you might see different formations. And, within that, you can kind of get into depth and look at that formation, specific qualities of the rock, where it's found, maybe, reach out to people who have been in that type of situation before, who've maybe drilled or blasted in that rock, and just gather further information once you kind of know what's on your site. The chart on the left-hand side, it's from an Alice Powder guide, kind of showing the properties of certain rocks in different areas. I'm sure there's many other publications for local areas that you can find depending where you're located. But for this one, specifically in the Midwest and the Western United States, it's showing the different rock types in these areas with their compressive strengths, their densities, and just kind of, more in detail properties for the certain regions where you might see this geological change. So gathering all this information on one platform, surveying a rock face with your drone and being able to analyze, some of the hardest information to gather in one place, which is the geological data and how you're going to apply that. It can be very difficult. And, having a 3D profile, excuse me, of your bench or your site, and getting that geological data, you'll be able to get the position of bedding faults, the orientation of bedding faults, and kind of understanding the location of certain problem areas within your face. This will help understand how the structure looks geologically and help in your blast design and planning. And also auto detecting seams and voids in geology before you load and be able to measure that in the column. The last thing you want to do is have a shot loaded and start realizing, hey, along my face, I might have some weak spots or bedding planes or joints, that could be an issue for fly rock, and poor outcomes. So kind of getting the location and the dip angles and the directions before, conducting your drilling and blasting operations can be very critical. And being able to do this, all on one platform can kind of benefit the time factor, where you don't have to have anyone else come in to kind of do a larger, more costly geological survey on your area of operations. So also with this AI detection, we can measure a lot of things within, the joints, shape, spacing, condition, distribution of major lithologies within your face, water content. And I like to point out here, getting that real precise location of where, these fault and damage areas are within your face. You can kind of see some of the images on the right here with a drill design, and being able to, with the AI, detect those areas within your face, where you might have problem areas, and measure that within your whole column can be critical. So, when you go to make your drill design, set up your driller for success, what to expect. There's no surprises. You can't always predict what's underneath the surface. It's guessing the impossible, essentially. So kind of getting an understanding what's along the face can help you understand what might be subsurface within your drill and blast operation. So when it comes to blasting and laying out your shot, a couple considerations I wanted to share with you guys. So as best practice, good blast design focuses on the jointing systems. And this is, orienting your face parallel to the direction of major jointing systems. Now, what does this mean? This essentially means you have three conditions, and you kind of want to match this best to your site. And I understand a lot of times you can't change this right away on your site. Some mines and quarries are set up where they've been shot this direction for years, and they're just kind of dealing with the outcomes as they come. If you ever have the luxury to start a new quarry or mine, or kind of shoot a new area in this pit, it's best to kind of look at how, areas in that pit might be reacting to the way that the blasting operations are currently happening. And a couple examples here. So shooting against the dip, with the dip, and across the strike. With the depictions shown below, shooting with the dip can lead to backbreak, yield smoother floor conditions. However, this can lead to some slip conditions along the face after blasting operations with backbreak is a risk. Vice versa, shooting against the dip can lead backbreak, but increase the possibility of a toe or kind of a rough floor. So depending on the site conditions, one of these could be better, give or take the pros and cons on your site. What might be better for the application. And then last, shooting across a strike. This could most likely should be avoided in most cases, depending on your site. It can lead to some safety concerns within the breakage of the rock, leaving some rough drilling conditions on especially open-ended shots. And this is where multiple bedding planes will cut into the face and can cause problems on the floor or within back break behind the shot. So a couple examples of this. This is a good example of shooting against a dip. So with this shot here, it was essentially there was a long bench cut into two different blasts. One of the blasts was cut where there was a bedding plane, essentially resulting in a kind of a poor breakage for the next subsequent shot. You can kind of see those undercuts on the open end there with a kind of a fat toe on the end. This led to some really difficult drilling and loading. There was quite a few seams on this open end, resulting in kind of a rough floor, as we talked about, shooting against the dip. And with this condition, choosing, if you're dividing, a long bench, say, into two different shots, choosing a good location to kind of cut one shot off and pick up the other, either if it's at a right angle with a square pattern or a 45-degree angle with a stagger pattern can kind of help you in the long run, not necessarily with floor conditions, but loading that next shot. You can see geology changes in this pit in the picture here. We have those darker dikes kind of striking up against the face. So kind of choosing a good location where to maybe cut a shot off or pick up another one can serve you well in further operations. Here's another good example, shooting with the dip. You can see a severe slip on the right side, on the face kind of on the left side. You can kind of see how the bedding planes and joints are kind of layered in there. And essentially this pit was being shot in one direction, resulting in these slips, which kind of caused a bit of a safety concern, but also more difficult drilling. The adjustment made to this pit was the face was turned to a different direction to adjust for these conditions. And because of this, the area of the slip was being diminished less and less as the bench moved back. So kind of understanding, getting a feel on how this rock is kind of reacting to the blasting going on site, making those adjustments if you have the luxury to do so, of reorienting faces to kind of favor the bedding and the jointing within the rock, can serve, for safety and productivity with the drilling and blasting operations. So here's a quick video, just kind of showcasing, yes, there's the AI-powered auto detection of these bedding planes, joints, and seams, but also the feature of being able to manually annotate these along your face. Right here, we can see there was a major seam, or bedding plane, excuse me, that was marked right along the face. Here you can measure the azimuth, the length of it, and further to that, see where that correlates within your whole column in a profile view. So as a blaster, I would want to mark these areas manually to kind of understand that dip angle, dip direction, and where that might intersect my column on the face. It's understanding this before you shoot, before you conduct that layout, like I said, can be critical in the prevention of things like fly rock. If there's weak bedding layers within your face that you might want to make different loading conditions to, or adjust your drilling, can serve you a headache down the road. So being able to mark that understand where it is accurately within a 3D or a 2D model, and then where that correlates within the whole column is essentially what we're looking at right here. So we kind of went over the site conditions, looking at the geology on your site. We're going to kind of move into the blast considerations now. So you're on your site, you kind of have an understanding of the rock, how it's breaking, what conditions might favor your operations on site, and after kind of designing your drilling and you have an idea of pattern and hole size, kind of get into to drilling. So pretty bold statement right here: rich and accurate drilling data is critical for ensuring optimal blast outcomes. And this is true in a lot of ways. You want to have accurate information. You want quality holes, drill to accurate elevations to ensure your best result. The elimination of kicker holes or inclined holes, if possible, keeping faces, as vertical as you can. Some applications you might be wanting to keep them at a certain dip angle and drilling at an angle, but for the most part, in most applications, keeping things straightened out and getting good drilling data to achieve the best results is kind of what we're looking at here. And here on the picture on the right, you can see a drill I worked with. This is a T45 drilling in an aggregate quarry. And this blaster in this site really toned in, his pattern and timing for the shots, and left some really nice high straight faces, I should say, and some hard rock granite. So nowadays, with the technology we have with these drills, especially with smart drilling, we really want to kind of dial in, accurate patterns. And when you have the luxury to do so, sending smart drilling or GPS data to drills to drill accurately, kind of within the centimeter of your design, where you want to know where that hole is being placed, where you designed it, and the conditions of the drilling quality from there. Drills know elevations essentially. The difference between depths and elevations. So to keep things consistent, especially within bench work, you want to send elevations to drill. So understanding, we're going to be drilling to elevation, let's say 100. That'll keep things consistent for the drill. That's the language the drill is going to understand versus depth. And as you maybe move a bench backwards or establish new benches, if you're kind of using the term depth and shooting a grade, kind of each time you have another shot, that grade might start to vary a couple feet depending on what location you're referencing. So kind of having a good design for a bench or within a mine and using correct elevations for your drilling can kind of give you a nice smooth floor at the end of the day and keep things consistent for digging operations. Consistent floor and quality control is kind of what we're chasing for consistency when it comes to drilling and moving the rock that we're blasting. Making sure holes are separated accurately for burden and spacing. Some site conditions, it's tough where you got to put, kicker holes in. You might have to shrink up your spacing in areas for access of the drill. However, keeping things trued up as best you can will serve for the best possible results. And again, keeping that back row straight. Not all applications, call for a perfectly vertical high wall. And it's tough to achieve a perfect high wall in most cases. But having the goal in mind to keep that straight, a nice stable high wall for that next shot, not only for drilling and blasting purposes, but for safety as well. So doing a digital drill design, optimizing your pattern, we'll say, having this design done beforehand, after you've analyzed your site conditions, the geology, kind of, tailoring your pattern to kind of fit your conditions, optimizing burdens, making sure you have adequate burden on the face in your rows to match your site conditions. This is critical. You get your information accurately done. Skip this slide here. And essentially sending this data to the drill through an IRDs file, so that drill knows exactly where to drill those holes, at what angle, what elevation, kind can save the accuracy and really place or achieve the results that you designed for, essentially. So this data, the measure while drilling data, with the smart drills, like I mentioned nowadays, not only with the GPS based precision they have, but recording the drilling data while they're drilling. So this is going to record, the color, the location, water, mud, voids within the column. It'll record penetration, feed, time to drill the hole, percussion, kind of all those physical drill characteristics. And then you have your hole placement accuracy. So you'll be able to compare, kind of plan versus as drilled once you receive this measure while drilling data and put it back into Strayos. So your starting angle, ending elevation, kind of comparing, plan to as drilled and getting real time changes in the strata within your column. We'll take this information and use it for our loading considerations down the road. However, gathering it right at the drill, understanding what you have subsurface for the geology and how that might correlate within the face can really help when you start looking at your loading of your shot. So we're going to look at analyzing this measure while drilling data. Specifically here on the left, you can see each hole is color coded, by penetration rate. Simple trends between the different measure while drilling metrics could identify soft or hard bands within the strata. For example, we have one right here. High feed pressure with a low penetration rate indicates a harder rock. You can also see the details in this kind of middle column picture of the plan versus drilled, how you might have deviation on the surface of where that hole was placed. Maybe it was because the driller couldn't access where that hole was originally designed. Essentially, you want to be able to see the differences there, how it was drilled, and what was in the strata. And correlate trends, where the hard rock on this bench might be versus the soft rock. So now we have our second poll question. So we'll take about 30 seconds here, answer this. How do you gather accurate bird measurements? I'm curious how you guys are gathering this information, whether it's a digital drill design or just kind of a pull and tape method. So I'll have Ravi open up the poll and we'll get some answers from you guys. Awesome. Ravi, you getting some answers? Keep it open here.
Yeah, so we'll close in about 15 seconds. We have a poll running and we're getting some good answers here.
Okay.
Meanwhile, just quick housekeeping. Can you hide that presentation, stop sharing bar?
Oh, yeah.
It's interfering with the presentation. Great. We'll give last 3 seconds. So still some answers coming in. Great. So it's great to see that the 3D measurements are becoming the mainstream here, which is majority of the poll answers. So we'll close now.
Awesome.
Thank you.
Great to hear. So I'll kind of touch on borehole probes and how this can benefit the drilling and blasting application, as well as measuring drilling data. I'm not too sure how common, everyone is familiar with bore tracking and borehole probes, essentially, and why it's done. So a borehole probe, essentially, it's a probe pictured on the left, with a compass and a kilometer. You kind of show the direction holes are going, and on a compass heading, and what incline that might be drilled at. This is information that post drill you'll lower this probe down a hole, be able to measure that data, in the depth of the hole and where, it's starting to deviate, where, you can pick up common trends within your bench, and just kind of getting that accurate drilling information post-drill. Taking this real-time data and then plugging it back into your 3D model can essentially give you your real-time 3D burden measurements along the face. Yes, you might have designed a certain shot. However, after some deviations within the drilling, your burdens are most likely going to change. And this is important to measure, especially in areas where, it's critical shooting. You might have structures around, worried about vibration and air blast. Understanding and measuring that accurate 3D burden is critical. And board tracking or not, having the 3D way of doing it, let's say a drone, is your quickest, most efficient, and also safest means of profiling that face. You don't have to worry about being on the floor with a scanner, where there might be operations moving around you. They're moving material, machines, and also 3D. You'll get more accurate burden points versus 2D. So I'm glad to hear that 3D is kind of the preferred method here that most people are using. And for safety wise, I talked about critical areas you might be worried about vibration and air blast. Fly rock, board tracking and using a borehole probe is critical in reducing fly rock. Understanding where you might have thin areas within your face will serve you well in the loading side of things, where maybe to stem some holes up, use a different product to load certain areas of the column, and this can prevent fly rock, in very important ways. So, you have your borehole probe data, and this is essentially an example of what that will look like. So you can kind of see the compass heading, north right now on that bullseye is going to point off your face, east and west, depending on how you orient your face. You can kind of see right here an example of a hole. As readings were taken throughout the column, you can kind of see how it deviates kind of the northwest direction at a distance labeled in feet. So this one is about 6 feet to the almost directly left, west of the collar. So you might have planned for a downhole. However, 6 feet of deviation, you're going to want to be able to measure that and understand where that hole is going. This is important, especially along the face, as it will provide an accurate burden measurement within your shot. And I want to touch on this with geology. The subsurface conditions are primary reasons that we'll see this deviation within the rock. It's depending on the drilling, the equipment used, the hole size, that can play an effect on how much deviation you see. But ultimately, the biggest uncontrollable factor we deal with is geology. And this is going to be kind of the governing factor that creates this deviation. And being able to measure it can be critical. So here's an example, a board tracking and a drilling example of some extreme deviation. This bench kind of had a consistent geology throughout most of it, that you can see all the holes deviated hard to the right. This was about a 65, 70-foot bench. You can kind of see the blast design up top for this shot. And we were seeing deviations anywhere from 15 to 20 feet directly right every hole. And, understanding this information before loading a shot is very critical, as it was a road about 1,500 feet in front of the face, kind of with no obstruction. So it was a wide open shot where fly rock could have been catastrophic. The driller, he was aware that his drill steel and the holes were deviating, but not to this extent. After using a borehole probe and measuring this data, we were able to really see where the holes are moving and how that adjusted the burden and spacing between the first and second row holes that we were interested in. Getting this data and then applying it to our loading and timing was also critical, as it's very far from the design shot that we had. So kind of an example, we'll kind of look at how this adjusted the loading within this shot, understanding where the holes deviated, where there were some seams or joints, and actually some holes came together at some points at the toe. So this was also critical to know, as when you're putting explosives in one hole and then seeing it rise in another hole, that's a big red flag. So understanding where those locations might be was very critical in this case scenario. And geology did have a direct effect on the quality of the drilling in this pit. The drill steel, it was consistent, but it constantly went to one direction. And the face burdens luckily stayed, within the range we wanted, thin in some spots, thick in others. But for the most part, understanding where the bottom of the hole was relevant to the next hole or the row behind it was the most critical to adjust our timing and our loading practices. You can kind of see on the top picture here, throughout some of these areas where there were seams, we would use a packaged product versus an emulsion or an ANFO. And also within our face burden in the bottom picture, what we plan to have, 9-10 feet of burden, we now have 5 or 6 feet. So we might be holding our product down a little more than we initially planned to along the face holes. Then we'll kind of get into timing. So, the initial timing plan for this shot, was kind of, spelled out in a way that, we had a good idea what we wanted to do for timing. However, looking at that real-time drilling data and the borehole probe data that we collected, kind of made adjustments to that on how, we might want to speed up our timing a little bit on the face, slow it down in other areas, kind of really tailoring our design based on the real-time conditions. And this is all due to the geology on this site kind of changing the original plan that we had, and being able to measure that and adapt to it, make the changes for the safest outcome. This shot ended up coming out great. Good fragmentation, no fly rock, which was our main concern after looking at that borehole probe information. So overall, being able to collect the data, bring it all into one place, and kind of carry out the loading and the timing and the measure while drilling data was a huge time saver, but also saved us the cost of a potential fly rock or excess of oversize within the shot. So some loading considerations. I know I used some of the example there, but being able to measure, where there might be joint planes or weak bedding planes, voids within your bench, subsurface will play a direct effect on how that's loaded. Gathering this information from not only a 3D scan, but also having good, accurate drilling information from your driller will play a huge part in understanding the location of these problemsome areas. Some best practices I put here: if you run into certain areas like the seams or the voids, you want to check that powder level in the column. If it's coming up at an appropriate level, if you're losing powder down the hole, where you might have a seam or a void, understanding where that might be, putting a hole tape down and taping it, making sure that powder rise is consistent. If you're operating with, say, a bulk truck or an ANFO truck, communicating with the driver, pressures and product totals per hole they're putting into the ground. So you're not putting excessive powder where it might be going into, a seam or a void, and understanding where those areas might be, because you could run into it on the very next hole if you find it in one. Also lowering packaged products into the hole with, say, a hole tape or a rope to prevent hangups in the column. If you have some broken, fractured rock on, say, the top third of your column, making sure you're lowering packaged product down, appropriately, and making sure it reaches the point of the column where you want it to, and nothing's getting hung up, no materials coming in on top of that, and making sure you have a consistent loading throughout your column, and if you ever need a deck, so we get into different ways of decking holes, whether it's stemming, air decks in certain areas, through these problemsome areas, and repriming where necessary. If you're putting excessive packaged products within your hole, if it's a wet hole, you might want to reprime, choosing the proper priming products for the products that you're using. Are all good practices when you run into issues subsurface within the geology. So you have your shot drilled, loaded, timed, you blast, successful blast, fingers crossed. And, we're going to look at fragmentation. So within varying geological conditions, you're going to have some different fragmentation, harder rock, softer rock. I bring up the term hero rock. Essentially, these final outcomes of the shot will kind of all come into play based on what we went over before: the site conditions, the rock characteristics, your blasting direction, the drilling, and the loading. There's some areas where within your bench, you might have to adjust your pattern or have to adjust your hole size and the powder factor. You might have stuck to one pattern on one side of the bench. You might encounter some softer rock. You can adjust your pattern, maybe gain a foot of spacing on that. If you have an obscure face, you might want to add a couple helper holes along that face, maybe at a smaller diameter, and just kind of tailoring these solutions of the geology to your bench conditions, and it's essentially achieving the fragmentation desired. Depending on the application, it's not always great to dust the rock. You don't want too many fines in that rock. You also don't want excessive oversize. So getting kind of that sweet spot and achieving your best blast results from adjusting all the factors that we kind of touched on and being able to measure that. Here you can see the AI detecting that rock fragmentation size and giving you, the actual fragmentation graph measuring the diameters of your muck pile and kind of understanding, what areas of that shot maybe broke better than others, and being able to measure that shot after shot. So your machine learning will essentially give you a better prediction model come future operations. We have our last question here, poll question 3, and this is regarding ground vibration. So do you use any ground vibration prediction software or tools prior to blasting? So we'll take a few seconds here and get some feedback from you guys.
We'll leave for 30 seconds. Very interesting responses here. So still there is a lot of tools out there to measure the ground vibration, but good to see the trend that the software has been amplified here, along with the Excel sheet modeling as well.
Awesome.
We'll close the poll in 5 seconds. Great. All right.
Thank you. Yeah, so appreciate the feedback. We'll kind of look at some options here. So, with ground vibration, especially in varying geological conditions, rock is homogeneous. So it's not going to be consistent. Subsurface conditions are not always known. And this is going to have a direct effect on how ground motion waves travel through the rock. The difference in, the presence of joints, faults, and fractures can really scatter peak vibrations in the direct path of ground motion. The influences of rock mass characteristics, especially on the ground motion, is very complex. This has led to the formulas we use to predict peak particle velocity, depending on certain site factors. So whether it's K factors, you're designing your blast for certain scale distances, and getting a good PPV prediction based on your blasting operation. So, you can see calculating PPV here with your K factor and your scale distance. And also, say a scale distance of, take for example, 50, if you're 100 feet away, that gives you 4 pounds for a charge weight, essentially. So, giving your range of your scale distance, your applications of your blasting operations in your closest structure, kind of getting all these variables put together and being able to get an accurate ground vibration measurement will be critical, especially when you have varying geological conditions on your site. So gathering this accurate vibration prediction. So I'll touch on machine learning here and how prediction of the vibration for each blast can kind of tweak your blast pattern to avoid possible damages. So having an understanding of, if it's a test blast, you have your first initial blasts on site, starting to gather that accurate PPV reading, accurately setting up seismographs, gathering accurate data to then input into the software and really gather, future accurate results. Automatically generating an accurate prediction for future blasting will be critical to avoid these possible damages. Getting accurate measurements to structures and really getting, whatever products you may be using, understanding how it's going to react essentially and monitoring this. So you have your seismograph set up at certain locations. As you input this data, blast after blast, machine learning will pick up the trends and kind of give you a better prediction come future blasts, so you can further improve your operations. Essentially, if there's adjustments you can make to your blasting to maybe pick up, shoot more pounds per delay if needed, expand your pattern or hole size. This can all kind of lead to further into the operational field. So lastly, I'll just kind of go over a summary here, a few minutes to do a quick QA. So we went over the geology on site, kind of reading what you're dealing with on site, and how that's going to impact, your drill design, your timing and loading of your blast. So how that's going to tailor specifically how you're going to carry out your drill and blast operations, and how the geology plays a role in ground vibration and fragmentation from blasting operations. All these factors, any site's never the same. It's very rare you're going to run into using the same conditions for every site. So kind of understanding, getting good visual inspections and gathering accurate data, whether it's references, indexes, drilling data from your driller, and really kind of planning for the best possible outcome on what the required result is within geology is the ultimate goal. So I want to thank you guys. We'll kind of open up for a quick QA here before we wrap up.
Great. Well, thank you, Eli, for the amazing session here. Certainly, there's a lot of useful information, kind of how the geology plays an effective role in each step of the process, and what are the tools out there that can be applied here. And I think the key factor here is what I'm seeing the theme is the data. The more geological data you can bring to your design process, the better you can understand the whole consideration and the final outcome here. So thanks again for the session. Thank you to the audience for sticking around here. We have quite a bit of Q&A here, so I will kick it off. If we don't get to all the questions, we'll make a response and email them since we have only 5 minutes left. So let's begin. The first question is, which is more effective, blasting vertical holes or inclined holes?
Yeah, I think that's strictly based on the application. Ideally, vertical holes, you design for a vertical hole in most cases to make sure you have consistent burdens if that face you're shooting is vertical. Depending on I've seen quarries and mines where, they choose to shoot holes or drill holes at an incline because that's how the rock breaks more consistently behind it. So, that's very tailored to the application. As things are designed for a vertical hole to leave a vertical face, that kind of keeps things trued up and be able to read accurate burden measurements along the face for planning purposes. So to answer that question, I think it's very site specific. I think in most applications, vertical holes are what people plan for, but there are special applications for inclined holes.
Yeah, the next question is, Strayos can use a common data to communicate with GIS and other blasting softwares. Can can we use large, I think in this case it's point cloud or shapefile or TIFF files? Does it have a size limit to this kind of files? So I can answer that. Yeah, Strayos can accept the data in a form of point cloud, which is .las or .ply, shape files or .tiff files. There is no limit to it at this moment. You don't need to do size reduction on the files. It can accept it. The next up question here is, how do you consider the jointing when determining your subdrill?
Yeah, so depending on the conditions, in kind of your pattern, how much spacing in subdrill you're planning for, kind of adjusting for the joints. If it's below or above the joint, kind of placing that bottom grade of the hole or elevation, I would say. Again, kind of site specific. When you're looking at joints and how much subdrill, you want to make sure that the ratio essentially of when you're designing subdrilling, you're meeting that ratio of burden to spacing, and depending on the application, where that rock breaks, if you find that the plane on the floor of the joint where that rock breaks consistently, that might change your subdrilling within the shot or within shots on the bench. So kind of understanding that shear plane where it might break cleaner than other areas or elevations on the bench would probably be the best practice for kind of adjusting subdrill with jointing.
Great. The next question is, I see this question has already been answered by Keith very succinctly here, but I'll repeat it anyways. How do you incorporate borehole probe data into Strayos? Is it able to display a borehole as a segmented line, not just a straight?
Yeah. So importing borehole probe data into Strayos, it's fairly easy. You gather your information, plug it into Strayos, and it'll give you that real-time 3D burden measurement and profile. Ravi, for the end of that question.
Yeah, so I think that the following question is it able to display a borehole as a segmented line? I think the question is it only displaying collar and the middle and the toe, or is it you can select your kind of different intervals to display the data?
Okay, yeah. So with the 2D and the 3D burden, especially the 3D, it's going to choose the kind of least path resistant, along that face, and the intervals can be adjusted kind of depending on how you collect, where you take readings within the hole. So those adjustments can be made, but essentially the 3D and the 2D are going to pick the least amount of burden within that column, wherever it may be.
Great. So we'll do one last question. So we are on the top of the hour. So the question is, how will you consider all this in pre-splitting, since that is a key in determining your bench face angle?
Yeah. With the pre-splitting, understanding, kind of like we talked about the site conditions, what kind of rock you're dealing with, and if there was any test drilling that was done prior, gathering that information so when you go to start drilling those pre-split holes, you know how that rock might react and how to adjust, so you don't drill a large amount of pre-split and then to come understand that it either deviated or was drilled at the incorrect angle. So maybe understanding where your bedding planes are, the dip angles, and how that might affect your pre-split drilling can kind of play into effect the outcome of it. So gathering the data and measuring it maybe early on before you run into an issue when you're pre-split drilling, maybe near completion. It would be, I would say, the best means of adjusting for the geology.
Great. I'll make an exception because it's just last. We got one more really interesting question. So
Yeah.
The question is, when considering the geology, I have run into cases where the rock in the upper portion of the shot is much harder than in the lower portion.
Mhm.
This consistently results in oversized material from the upper portion of the shot. Do you have a favorite strategy to mitigate that? And the question is from Mike Conley.
Yeah, a typical term cap block, we like to say. I've ran into it a lot, and I think some good practices I've come across is, depending on what you're loading as primary explosive within your column, as you come into that cap rock, let's say on the top third or 10 feet of your column, maybe using a package product, a stick product, or doing a quick deck with maybe a booster to kind of break up that cap rock if it's just a small amount. But I would say adjusting your product selection if available, and maybe putting a deck in to break up that top layer of cap rock, whether it's a small diameter stick product or larger diameter, even just maybe a larger booster or primer to kind of break that up. I have found to be effective in that issue.
Amazing. Well, thank you for, again, the questions here from everybody in the participation slide. Always great to engage and kind of just understand how everybody is, operations are doing here. So now we will wrap this up. Just one final comment. We will be at ISEE conference in next week. So see us there, see us, our team. Would love to meet you in person. Stop by our booth at 704 and 706. Meanwhile, if you have any other questions, email us. Elijah's email is there. Until then, well, thank you everybody for joining in today. Hope you have an amazing day and amazing week. Thank you. Bye.
Thank you, everybody.